Alright guys, so we did the basic vectors yesterday. We're going to look at the geometric problems today. So these are where you're going to have to start thinking about, sort of like you did at GCSE, there's always a shape involved somewhere and you follow it with the vector it's positive against the vector it's negative and so on, but just a little bit more complicated. So you've got A, B, C and D are the points given in the order. So this one's point A, point B, point C, point D. We want to find A to B and D to C. Now remember, for the first one, A to B is the vector from, or the vector to B, so that's OB, because remember they're all rays from the origin, minus the vector to A, so minus OA. So first of all, we need to know what OB and OA are. So there's my A, there's my B. So O to A is obviously this written in vector form, so you can, if you want, just use it as column vectors. Usually makes it a bit easier. And O to B is this one in vector form, which is just 1 minus 7 minus 3. That means that what we end up with is 1 minus 7 minus 3, subtract 2 minus 5 minus 8. And so 1 subtract 2 is minus 1, minus 7 add 5 is minus 2, minus 3 add 8 is 5. So I've got the vector AB. We're going to do exactly the same with DC. So first of all, that means O to C minus O to D. Because remember, D itself is just a coordinate. O to D makes it a vector. Okay, so if we find O to C and O to D, O to C is then just 0, 15 minus 10, and O to D is 2, 19 minus 20, both just the vector form of the coordinate, because all you're doing is taking away the origin, which is obviously 0, 0, 0. So that makes it the OC one, which is 0, 15 minus 10, and we're subtracting 2, 19 minus 20. 0 subtract 2 is minus 2, 15 subtract 19 is minus 4, minus 10 add 20 is going to give you positive 10. We want to show, okay, they want it written in this form, which is not ideal because I didn't leave enough space for that. So that means that AB has to be equal to minus 1i, remember you're underlining for a vector, minus 2j, and then plus 5k, so that's this written in IJK notation. And D to C is then minus 2i, minus 4j, and plus 10k. And then it says, show that lines AB and DC are parallel and that DC is equal to 2 lots of AB. So what we can say is DC is 2 lots of minus I minus 2j plus 5k. Therefore, DC is equal to 2 lots of AB. Hence, they are parallel. So remember, from GCSE, 2 vectors are parallel if it's the same vector, they're just multiples of each other. So it just means DC is twice the length of AB. Okay, and then hence describe the quadrilateral. Well, if you think about it, you've got 2 parallel sides of different length. So I've got a shorter one and a longer one, which makes it automatically, if you're joining it up to form a quadrilateral, you've got a trapezium. So describe the quadrilateral, trapezium, and then you just put as 2 parallel sides of different length. Sorry, run out of space on that one to fit it on the page. Right, example 2, you've got P, Q and R are the points as given. Find the coordinates of the point S so that PQRS forms a parallelogram. First thing to be careful of is that these are always done in the order that the letters are written. So that means if you drew a parallelogram, okay, and you started at a point, you've got P, Q, R, S. Notice that they go all the way around the shape, okay, in the order that they're given. So we know that if I was to write these in vector form, P would just be 4 minus 9 minus 3. Q would just be 7 minus 7 minus 7. R would be 8 minus 2, 0. And S we're going to work out. So I'm just going to label it X, Y, Z. Okay, so I've got my 4 points. Find the coordinate of the point S so that PQRS forms a parallelogram. Now, if you think about it, these are obviously outer P, outer Q, outer R, outer S. Okay, because remember the vector is from the origin to each one of our points, each one at a time. Okay, if we want to get from, back to the idea, we've got a parallelogram. So I've got that side and that side have to be parallel and the same length. That side and that side are parallel and the same length. So we're basically saying if I go from O to Q and then Q to P, that would be the same as O to R and R to S. This distance, basically what I'm trying to say, let's say that a bit better. This distance here is obviously the same as this distance here. So if I can work out Q to P, I can then just go, well, O to R and R to S. So Q to P is obviously P minus Q. So we're going to do 4 minus 9 minus 3, subtract 7 minus 7 minus 7. And just because we're working in vectors, I'm drawing that direction. So Q to P is 4 minus 7 is minus 3. Minus 9 add 7 is minus 2. Minus 3 add 7 is 4. So I've got that vector from Q to P. Because I want to find point S, basically if I went from the origin, I know this sort of overlaps my workings, from the origin to R, which is O to R, which we've already got, and then all I want to do is add on the vector Q to P, because this vector here is exactly the same as this vector here. I've just started the vector at a different point to where I started last time. So if I want the point S, all I want to do is, if I want to go from O to S, all I'm going to do is I'm going to go from O to R first, and then I want to add on R to S, but R to S is exactly the same as Q to P, which we've just worked out. So O to R first of all is 8 minus 2, 0, and then I want to add on Q to P, which is minus 3 minus 2, 4, in which case 8 add minus 3 is 5, minus 2 add minus 2 is minus 4, 0 add 4 is 4. And there you go, I've got my vector from O to S, so that is the position vector of S. Right guys, next part, so sorry, just knocked the camera there. What we've got is a little bit more information to add to the one I gave you yesterday. So coplanar vectors are vectors which are on the same plane, and it will be described in the question. These vectors are coplanar. Non-coplanar are vectors which are not in the same plane. Okay, all you need to know is that if A, B and C are vectors in 3 dimensions which do not lie on the same plane, then you can compare the coefficients on both sides of an equation. And we'll discuss that in a bit more detail once we get onto the mechanics and how all this sort of stuff works. But that just means, for now, all I need to know is that because these ones are, I can equate coefficients. So I can say, if I look at the I terms on both sides, 3 has to equal P. So that's looking at the I terms. If I look at the J terms, P plus 2 has to equal minus Q. Well, we know P is 3, so 3 plus 2 equals minus Q, in which case Q equals minus 5. And then if I look at the K terms, I've got 120 is equal to 4PQR. So I get 120 equals 4 times 3 times minus 5 times R. So we get 120 is 4 times 3 is 12 times minus 5 is minus 60R, in which case if I divide by minus 60, R equals minus 2. And that's it. Nice and straightforward. You get your point P, Q, and R. Right. This last question, I've never actually seen a geometric proof come up in an exam, but you never know. So this one is just a little bit trickier. It's kind of a lot of thinking in this one and a lot of imagining sort of what's going on. So you have to be very, very careful with your letters. Okay, so you've got your cuboid from A to G, or O to G in this case. Okay, A, B, and C are the position vectors of the points A, B, and C. So it means if I go from O to A, we give it the position vector small a. O to B, we give it the position vector small b. O to C, we give it the position vector small c. Okay, we want to prove that the diagonal from O to E, so if I were imagining to draw a line from O to E and a line from B to G, so okay, that point there where they intersect bisect each of the lines. So it basically means it should cut that line exactly in half and that line exactly in half. So for now, we're going to give that another letter. And since we're up to G, we'll call it H. Okay, so basically, we know that from O to H, okay, that has to be some multiple of the line O to E. Okay, so O to H is some multiple of the line from O to E, and we basically want to be able to prove that R equals a half. And then if we look at the other one, we know that from the other side of things, that B to H has to be equal to some multiple, but again, we don't know what that multiple is, so we've given it a different letter, is some multiple of B to G. Okay, so we've got all of our facts there that we need. And what we're going to do is basically, if I look at what I can rewrite, so I know O to H is equal to some multiple of O to E. I can also say that O to H is the same as if I went from O to B and then B to H. That's exactly the same distance, or got me to exactly the same place as going straight there. So I could say that is the same as O to B plus B to H. Now we know O to B is just the small vector B. Okay, and B to H we've already described as some multiple of B to G. Okay, so I know those parts first of all. Now B to G is something I can describe all the way around the graph. So if you think about it, if I wanted to get from B to G, if I just write that on this side, B to G, I could go minus B plus A and plus C. Because obviously I've gone against this arrow, I've gone with this arrow, and then this side here is the same as this side here, so I've gone with that one. So I've got minus B plus A plus C. Okay, and what's our other one? Okay, so because I know O to H can be described as some multiple of O to E, I can write some multiple of O to E. This way I've come up with basically an equation that's got both of my missing letters in, which is what I'm aiming for. Okay, now O to E is another one we can describe just by working our way around the shape. So O to E I can describe as A plus B plus C, because I'm just going with each of the arrows every time. So A plus B plus C. If I just go through that one again. So O to A would be A, and then if I go to D, that's the same as this one, so plus B, and then from D to E is the same as this front one, so plus C. Okay, so it's a lot of kind of imagining what's going on. That means I can now replace all of this. I get R is some multiple of A plus B plus C. Okay, that has to equal B plus some multiple of B to G, which we said is A plus C minus B. Remembering to underline everything since they're vectors. And now all we're going to do is, just like we did in the last question, we're going to equate coefficients on either side, and I missed a plus. Okay, so if I look at the A's and the B's, now if I look at the A's on this side, I've got R lots of A. So R is equal to, that's not an A, so I don't have to worry about it, is equal to T. So I know R and T have to be the same value. If I then look at the B's, the R on this side has to equal, and I've got 1B outside, and then I've got minus TB, so minus T. Okay, I've got a pair of simultaneous equations. So if I replace R with T, I get T equals 1 minus T. That means 2T equals 1. So T equals a half. And therefore, if T is a half, I can plug it back into there. R equals a half. And so you've proved that that point H is halfway along the line O to E, and point H is halfway along the line B to G. And just to check that they actually intersect, all you need to do is basically plug that value into the C's to make it work. So on this one, you get R has to equal, there's no T's there, it's just T. And since R is a half, T is a half, it works for C. So therefore, they intersect at H. No, sorry, battery's dying. Intersect at H, and I've forgotten what I was writing. Intersect at H and H and bisect the lines. Okay, sorry about that, guys. Sort of phone died at that point as I was recording, but that one is the trickiest it will get. Don't concentrate too hard on that one. We'll spend a lot more time on those ones as long as we're happy with the rest of it. Have a go at exercise 12C, I believe.